start time to 5:30 so that we can start at 6 to make it a little bit earlier. Well, it almost worked. Anyway, I would like to welcome everyone to the Spring 2017 Regional Movement Disorder meeting. And before I proceed to do anything else, I'd like to thank our sponsors who helped this program, including AbbVie, Acadia Pharmaceuticals, Allergan, GE Healthcare, Impex Labs, Lundbeck, and US WorldMeds. And I'm not sure if Allergan is a sponsor, but some of them are here. So in any case, we are thankful to the sponsorship and the wonderful help with this important program. As you know, today there will be only one talk. Normally we have two featured talks, but I got the privilege of going a little bit longer. So don't copy me in terms of how long it's going to go, because that's never going to happen again. Stick with 10 minutes. So this will be a little bit longer, and I hope that it will be worth your while, except the video cable is out. So with that, I would like to proceed to today's presentation, which will be about disease modification and some of the targets in Parkinson disease, some area that is very hot and very popular recently. I'm not sure if our Georgetown friends are here. They are also very much involved in nilotinib as well. First of all, I'd like to thank my collaborators and colleagues who helped with this work. And this includes Han-Suk Ko, who is an investigator with the Institute of Cell Engineering, as well as Dr. Soki Lee, who is in radiology. We are all at Hopkins. And we also have some additional collaborators who are part of our team. We actually have a spin-off company that is separate from Johns Hopkins, and we named it Neuraly. And Neuraly is a incorporated company with the leadership shown here, as well as the advisors of our team. So I wanted to give all the credit to everyone who has been involved with the work that I'm going to show you today. So today I will first introduce to disease modification by certain concepts that are relevant to how to research disease modification. And so we have had this idea of Parkinson's disease being a single disease, and the research criteria have included a clinical tier. So we have MDS clinical diagnostic criteria now. By the way, I thank Dr. Espay, who shared these slides, and the reference is down there. It is a Nature paper from earlier this year. So we have the pathological tier. We diagnose Parkinson's disease by pathological criteria. Then we have the genetic and molecular tier. And then it creates a little bit of confusion as to how the prodromal symptoms phenoconvert to a single disease. So this slide shows some of the biological systems that have been previously identified as playing a part in Parkinson's disease. And of course, these are the biological systems that we target for trying to change the underlying pathology and finally come up with the disease modification therapy in Parkinson's disease. The reference is on the bottom of the slide. So the idea is that we have all these different biological systems that we have identified over the years in the pathogenesis of Parkinson's disease, and somehow all of them contribute to what we know Parkinson's disease and characterize Parkinson's disease by: the Lewy bodies, the Lewy body pathology, synuclein pathology, as well as the dopamine loss. And this sort of reductionism led to the idea that when you characterize any one of these molecular subtypes, you can actually reverse it and find ways of developing disease modification therapies from that knowledge. So that doesn't really work in actuality, because if you look at the history of disease modification trials, then you find that we have had phase 3 trials, that some of them are really big ones. Think about the creatine, the NetPD LS1. 1,745 patients enrolled, failed. Everything else failed. So is there a problem? I mean, 0 out of 17 is not a very strong story in terms of success. There are many other attempts and efforts that are currently ongoing. We are part of some of them, including isradipine, which is the steady PD, including inosine, which is the short PD, and so on and so forth. Now, I would like to draw the attention to the GLP-1 agonist work, and I would like to make an argument that how we pick the targets could be very relevant in terms of the universal applicability of our efforts. So I would like to talk a little bit about the biomarker development work. In the current model, we have a clinical phenotype, and we hope that we can validate biomarkers from there. On the other hand, Dr. Espay is suggesting that it should be the ideal model where we identify biomarkers and then we make sense of them in terms of molecular phenotyping. And with this, you would have to have a much more customized and in the precision medicine individualized approach to treatment. So in that sense, you can kind of come up with a treatment for every single patient. I think that there is something common within the Parkinson disease group, or even beyond that. And then there may be some targets that could actually be shared and common across all of these disease types, or beyond that. And this common target is what my talk will be today. So we have had some information about how the neurons and oligodendroglial die, and the role of microglial as well as astrocytic activation in that. This paper came out recently in Nature. Dr. Dawson, who is also a collaborator in this work, was a co-author. And this was a really significant paper that found that microglial activation is necessary for the A1 astrocyte induction. And this is a key component of how neurons die in various neurodegenerative diseases, as well as trauma and other injury. And this activation of microglia, if prevented, pretty much eliminates the neuronal and oligodendroglial death. So the way we think about it is microglia are critical in the process of neuronal death, and cytokines that are produced by microglia, including interleukin-1 alpha, as well as tumor necrosis factor, and the component 1 part Q, are all critical in this process. Those are necessary for the A1 astrocyte activation, which will then eliminate neurons and oligodendroglia in all these diseases. And this story has been fairly well established. Now, when I mentioned exenatide earlier in terms of the GLP-1 agonist work, I should say that we have found a pegylated version of exenatide that was discovered in Korea. We termed it NLY001, that is much more potent than exenatide and works in cooling down the microglia in a way that far exceeds what exenatide or any other GLP-1 agonist can do. It cools down the microglia, and therefore it's very well. I have some supplementary slides if I have time for that, where it's shown that by activating GLP-1 receptors, which actually get expressed on microglia in the time of injury and neurodegeneration, there is a almost complete stop of the production of these cytokines that I mentioned, and therefore you can eliminate the induction of A1 astrocytes almost completely and salvage these neurons. So I would like to show you some data in this regard, and the first one is a transgenic mice model. I don't have a pointer, but I can just tell you. So in the left upper corner, it's a survival chart. So you can see the survival of the transgenic animals injected with saline, and kind of all of them are dead by 14 months. And you can see that the ones that are treated with NLY1 survive much better. And in fact, you can see that we saved the life of one normal animal with NLY1 there too, which speaks to perhaps the normal aging effect of NLY001. It does block gliosis, and you can see that the activated microglia marker, which increases in the transgenic mice, can be reversed with NLY001. And then in another animal model where fibrils of synuclein are injected, the PFF model, we have a behavioral test, the pole test. The longer the time, the worse. So the pole time increases in the animals. These are wild-type animals that are injected by PFF. And you can see that in the animals that are injected by PFF, the pole time increases, and then it almost normalizes in mice that are also treated with NLY001. And in the right lower corner, we show that NLY001 also prevents the alpha-synuclein aggregation and Lewy body formation in these PFF-injected animals. This is the pole test, and I will test if. Oh, you know what? That's not the laptop. I have it on Wi-Fi here. But anyway, so basically, this is just to show you how the treated animals actually normalize after treated with NLY001. So this is the experimental design for the PFF-injected animals. So they are 3 months old. At that time, they are injected with PFF, and then they are injected or treated rather with either the saline or the NLY001. And then all the behavioral tests are done after that, as well as the body weight and biochemical studies are performed. In the lower panel, you can see how the various behavioral tests demonstrate that once NLY001 is applied, then the animals are almost normalized. This is the genetic model that I explained earlier, and that's kind of the experimental design for that. And then this is the slide which demonstrates the microglial activation in vivo. So you can see that the microglial density and the microglial markers increase after PFF was injected, the fibrils were injected, and that effect is completely prevented or almost completely prevented with NLY001. This also demonstrates that those 3 cytokines that I mentioned earlier are clearly induced, or their production is increased in the PFF animals, and that increase in the cytokine production is prevented by NLY001. This is an in vitro experimental model where we demonstrate that the washing fluid from the isolated microglial cells can induce the astrocytes, and they can induce neuronal death after that. And using NLY-001 prevents the effect of injecting the PFF on them. So this is a quick summary of the animal data. In the PFF mouse model, which is considered by many as the best animal model right now for Parkinson's disease, because these are wild-type mice that are injected with these fibril fragments, and they develop very clear synuclein pathology. So in that model, NLY-001 actually prevents the abnormal behavior that's induced by the injection of these fibrils, and it also prevents the alpha-synuclein pathology as well as the neurodegeneration. We also showed that in PFF-induced microglial activation and secretion of these cytokines in vitro is reversed. We also showed that in the transgenic animal model, we extended the lifespan without causing any problems. Some of the GLP-1 agonists cause weight loss, and our animal models didn't really show that. And overall, the consistent finding across all of these animal model data is that it seems like NLY-001 prevents inflammation, production of cytokines, astrocyte induction, and neuronal death. So I'm going to switch gears just a little bit for the last couple of minutes of my talk. And I also wanted to share that in preparation of our clinical trial testing, another very important finding occurred at Johns Hopkins. This is courtesy of Dr. Martin Pomper, who discovered this microglial tracer called DPA713 that has a much cleaner signal than any first-generation microglial markers. This is a picture from a recently published study on NFL players where normal controls are compared to those who had head trauma, and shows a rather widespread and very clear, and this is only from like six controls and patients. So even in a small number of patients, you can see a very strong signal in terms of microglial activation. So we are hoping that at least as an exploratory outcome measure, we could use this tracer to follow microglial activation. We make the assumption that from all the previous data, as well as that Nature paper that I showed you, microglial activation, the level of microglial activation could determine Parkinson pathology or correlate with it. And we have done many autopsy analysis at various stages of Parkinson's disease with Dr. Dawson, where we found that at any stage of Parkinson's disease when patients die, the microglial activation correlates with synuclein pathology. So in other words, microglial activation could be a best marker to track disease activity, and it could be a particularly good outcome measure for our studies where we base our disease-modifying effect on cooling down microglial activation. And to close, I would like to show our proposed plans in our fundraising as well as clinical trial testing. We are at the moment preparing for an IND meeting, and we hope to get an IND to start clinical trial testing, first in toxicity, normal volunteers, phase 1 this year, and hopefully within a year or about a year from now, hopefully we'll be getting ready for our phase 2. As our main outcome measures, we would probably do some traditional ones like motor exams, but we also would like to use wearables as our motor outcome endpoint, and then as an exploratory endpoint, we will use the PET tracer, the DPA713 as well. And then who knows, after that, we may go to phase 3. So that's all I wanted to share today. I hope it's exciting, and we have time for some questions.
How does Marty Pomper know that he's finished? microglial activation? How does he know that?
So this tracer was developed in microglial models, and so you can actually have isolated microglia. You can inject lipopolysaccharide on them, and that's kind of standard activation. And so this is the PSBO marker that has been first developed in those experiments. So it's highly validated, and it's clearly a microglial marker.
On animals.
Right.
Yeah.
So I have a question about the sort of fundamental logic of this approach. I mean, it is a very interesting bit of work, of course, and it is promising in relation to sort of extending the duration of good life in patients with Parkinson's disease. But the sort of question is about the sort of fundamental logic of it. I mean, presumably there is something the matter with the cells that the microglia then are activated in order to kill. And that can be various, as you pointed out in the beginning. It can be a variety of different abnormalities that lead to dysfunction of the cells that then lead to an inflammatory response, which is then, of course, by itself problematic. And if you slow that down, the cells live longer. But is it going to be ultimately curative in the process? Is it the fundamental mechanism of Parkinson's disease, or is it just something that sort of speeds up the process of cell death of the cells that are already destined to die anyway?
So we don't know, but basically the hope is that there are always two processes at odds of each other, and when A1 astrocytes get the upper hand, then there's cell killing. But there are also A2 astrocytes which promote trophic and supportive functions, and so hopefully if you can tip the balance, they could get the upper hand, and restorative and salvaging forces will be able to do their thing. So I don't know the answer whether this is going to just cool the process down and forever and halt progression altogether, or just extends it or buys you time. We have to see what happens, but the brain does have some powers to right itself, and this way we could give it a chance to do just that.
So with this, are you basically what you're doing is decreasing the inflammation?
Basically, that's the kind of way of. I'm showing this slide here where we found that GLP drops in animal models as well as in Parkinson brains, and so that can be part of this process. And basically, what we're doing is that we specifically activate those GLP-1 receptors in a way that we can use with a subcutaneous injection every week. Because the other thing is that our compound has an 88-hour half-life, and we think that the area under the curve is responsible for why it gets into the brain, because we have a much better blood-brain penetrance than any other GLP-1 agonist. These are peptides. So it is somewhat specific to that process, and ultimately it is inflammatory markers that we are reducing. But at the same time, there are many inflammatory markers. There is interleukin-1 beta and others, which are irrelevant in this process. So we don't know exactly the degree of specificity, but it seems like that it's somewhat specific.
I have another question. In relation to the possible safety issues, if you dampen down inflammation considerably, would that potentially make you more prone to different types of infections?
As we see with MS and many other anti-inflammatories, there's always a downside to that, and so that's why we need to do clinical trial testing. So it seems to be very safe in animals. We have some monkey data where there were no reports of infections. We have tested up to 10 milligrams per kilogram in monkey, and that seems safe. And we think that in the human, probably 1 milligram per kilogram is going to be where the benefits saturate. So we have a very good therapeutic window, and of course we need to do testing to determine that.
I think Mark has a very good point, because that's what happened with TNF alpha blockers like infliximab, right? with even though there's systemic medications, you decrease the ability for inflammatory response in the brain, and then you're prone to getting tuberculosi, meningitis, and other infections.
But again, I just want to emphasize that it's not like a global, depressor of immunity and anti-inflammatory. I think there is quite a significant element of specificity in this.
So the treatment in these experiments was for 5 months, right? In the mice to show effect. Was there, like, what's the shortest time of treatment that shows a reduced inflammation in the brain of the mice? Because like 5 months to see an effect in the mouse is like a lifetime in the human life.
So you should observe them for longer.
No, I mean like the treatment, the NLY treatment was for 5 months, right? Before you analyze the data. Was there like a time point earlier to see if NLY is effective at 1 month or 2 weeks? Like what's the earliest time point this is effective? Because in the life of a mouse, 5 months is a very, very long time. So how does that translate to the human studies?
So that's a good question. So we don't know, ideally, if it works as an in vitro, then you could kind of shut down that inflammatory process. And so we hope that in the phase 2, we will see a signal on the PET scan 3 months after. Because that's the other thing, that most disease-modifying markers today take a very long time. When you have a few points in the UPDRS that changes over a year, and the noise of the UPDRS is about that much, and so that is not a very good outcome measure to track disease modification. If our hope works, then you could see the signal in 3 months. The UPDRS wouldn't change in 3 months, but if you shut down microglial activation and this PET tracer works, you could see that signal within 3 months. So we haven't looked at what if we just do it for a week or 2 weeks, and we don't have such experiments. Well, thank you very much.
Right, so let me make a comment. Let me make a comment. I have known Zoltan probably for longer than anyone else who's here, and as you may know, the reason that we gave Zoltan a little more time to talk today because this is his swan song. He will be leaving the area and moving to Las Vegas, where he has a very nice position with the Cleveland Clinic, running movement disorders there. I first heard about Zoltan actually when he was a resident, so it's a long time ago. He was working with Ivan Bodish-Volner on the visual system, and Ivan wrote me and said he had this very bright young resident who had this very good ideas, and could he come and do a little work at NIH as a part of his neurology training, and we were very pleased to have him come at that time. So he actually started coming to NIH when he was a resident, and then we were very pleased that he decided to match with us as a fellow in movement disorders, and came and worked with us for, I guess you were fellow for 4 years, that's right, doing movement disorders and a lot of very good physiology. And at the end of that period decided he really wanted to even learn more physiology, which is hard to imagine after after 4 years of us, but he actually then did a physiology fellowship in the EMG lab at the NIH. He spent 5 years altogether at NIH working with us. And when he was with us, not only was doing some good work in physiology, also around the botulinum toxin clinic, and learned all sorts of good things. So we were very pleased at the end of that training that he got a job at Johns Hopkins, where they immediately put him to very hard labor. I must say, I spoke to Zoltan from time to time during that period, and he was working from morning till night. Not only was he running the movement disorder activity, he was doing all the intraoperative monitoring, and he was running botulinum toxin and doing everything. And it is really terrific that he's moved up through the system so well there, and his great expertise, has been recognized with moving up to now been heading the movement disorder group there for the last number of years. He has been helpful, of course, in our local organization here, has been one of the organizers of this particular meeting, and I must say has given us a lot more organization in some ways than we had before. He's kept good records. We never kept good records of this. We've always had a good time, but we've never kept good records. Zoltan began keeping very good records of all the activities, a very good list of all the people that are here, and when you've been getting the announcements, they've been coming from Zoltan. So he's done extremely well, and this particular talk is a good sign of the very exciting things that he's been able to accomplish and deal with when he's at Hopkins. And we will certainly miss him locally, and we wish him the best of luck.
Thank you so much, Mark. I really have a lot to thank Mark himself and many people here, but Mark in particular for helping me through my career with advice to learn the tricks and the particulars where you have to focus. And of course, I worked a lot, and you can always just work a lot, and that will get you through. But also, I worked not just spinning my wheel, but getting good advice, and I really appreciate that. It is with mixed feelings that I move on, because this is the area and the people that I became who I am, and now it came to my career to move on. I got this wonderful offer that was very difficult for me to accept, but eventually, in consultation with my wife, it was the right decision to be made. And I like to stay in touch. I really appreciate working with all of you guys, and I hope that I can come back to the regional meetings. And Kelly Mills from our team is going to take over the organizing, and he's even a better organizer than I am. So that part will be a very smooth transition, and it will be always a great feeling for me to come back. And of course, if any of you come and visit Las Vegas, which is a nice place, especially in the winter, we have palm trees and things like that, you're always welcome to visit me. I'll be available and around, so I hope that you will come, and I of course see you at national meetings as well. So thank you again. I'm the host of this evening, so I'm gonna stay on after all this thank you and everything. Of course, I hope that this meeting will go on, and I can be a remote participant in the future. Thank you.